Okay, we're recording now, and it's week 5. So I'm talking about gravitation, and I'm concentrating on what's called astrophysics. I mean, nowadays it's actually been quite a while. Astronomers don't usually even, I mean, they use it kind of interchangeably, but a lot of astronomers don't call themselves astronomers anymore. They're astrophysicists. They apply physics to understand, what's happening outside the Earth. And of course, they can specialize in different things. They might be interested in the solar system, or asteroids, or comets, or the sun, or stars in general, or galaxies, or the whole universe. And that's a special group, and they call themselves the cosmologists. They try to, learn about the cosmos in general. So this started to become possible as a real science thanks to Newton. I mean, prior to Newton, astronomy was largely just observation, recording, where a planet was at a certain time of year, stuff like that. So let's go ahead. But we needed to know more to do more. So we can thank Newton largely for that. And these are figures. There could be many more here. In fact, I left out Cavendish. I'm going to mention him later, but these are important figures in history of gravitation. We have on the left here, if I remember right, I think it's Aristarchus. He was a Greek astronomer. He's the first person, this is over 2,000 years ago, and he's, at least in recorded history, perhaps the first person to suggest that the Earth went around the sun. In other words, that was the heliocentric model. Okay, the Earth and the planets revolved around the sun rather than the sun and the planets revolving around the Earth. But that idea didn't really catch on for about 1,500 years. And then Copernicus came along, this guy on lower right in Poland. So Copernicus knew a lot about astronomy, and there was something that I don't know if I can show it here. I'm gonna go out on a limb and fire up a program. This is unplanned, but it's important observation. This is an observation known since the ancient Greeks. All right, this is what I was trying to show in the live meeting from Thursday night, which wasn't recorded properly. So what I have here is a view of the night sky from my location in Indiana. And the time is set 11 o'clock at night, January 1st, 2025. I'm going to start clicking through the days. Now pay attention to the stars in the background. So what I'm trying to simulate here is if you went out every night and centered your camera so that Pollux, this star right here, is at the center of your field, and you orient all the stars to overlap where they were the night before, you'll see the stars remain in position, but Mars moves against the background. You probably also at some point see the moon moving across the field and maybe Jupiter. So let's go run this video forward. So as I go night after night, you see Mars is moving left to right, and then the moon sweeps through the sky. Now look what happens. Mars is slowing down and reversing its direction. This is why they call planets planets, because it comes from the Greek word planetos, which means wanderer. They wander against the background of the night sky. This weird motion of the planets not only moving against the background night sky, but reversing their direction, was easily explained by Copernicus with this heliocentric model. As the planets orbited the sun, when the Earth would pass Mars in its orbit, Mars would appear to reverse direction against the night sky. This is called retrograde motion. Maybe I can find an image real quick here. So here's a video. I'm just going to click on it and hopefully it's going to show what I mean. I'm going to play it at higher speed so we get through it more quickly. But you see the Earth going around the sun and passing Mars in its orbit. Now this line shows where Mars is against the background stars. It's your line of sight. Now you see Mars is reverse direction here. And then later Mars will go back in its normal direction, right to left. So this is what's happening here. So we're going through this quickly. So if it doesn't make sense, go back and find a video like this one, and it'll explain retrograde motion for you. All right. I might even include the link in the post about this video. So the ancient Greeks, most of the ancient Greeks, the more popular model had the Earth at the center of the solar system. And to make this whole thing work and explain that motion that you saw from Mars, they had to imagine that Mars not only went around the Earth, but followed a loop trajectory around the Earth. And those were called epicycles. Well, Copernicus was a little more skeptical. He said, what's making Mars do that? Why would Mars want to make such a weird motion? Let's just put the sun at the center of the solar system and let the Earth be closer to the sun than Mars is. And Earth is going to go around the sun because it doesn't have as far to go. It goes around the sun faster than Mars does. And every so often, Earth passes Mars. And from our point of view, as we catch up to Mars and pass Mars, its apparent motion in the sky is going to reverse direction. So he could very easily explain retrograde motion. The interesting thing is his explanation was simpler, but it wasn't any more accurate. Ptolemy, the ancient Greek, explained it with epicycles very, very well, actually, even though his model was wrong. But a lot of scientists following Copernicus's lead thought that, Copernicus had a better explanation. The main one is Galileo. Another important scientist in Galileo's time, who I left out, who's probably just as important as Galileo, is Kepler. Kepler studied the motions of the planets, and he established his laws of motion. And without those laws of motion, planetary motion, this guy on the upper right here, Newton, could not have come up with his law of gravitation. Because for planets to follow elliptical paths in the way that Kepler described them, there had to be a force that had a strength inversely proportional to the distance between the planet and the sun. So, Earth is roughly three times further from the sun than Mercury is. And for Mercury to go around the sun in that tight orbit that it has, the force of gravity has to be about 9 times stronger than it is for Earth. That's inversely proportional to distance. If you're closer, the force gets stronger. If you're further away, the force gets weaker, but it's not proportional. If I double my distance from the sun, the force of gravity gets 1/4 as big. Okay. And that had to be the case to make Kepler's laws work. And Kepler's laws were based on very careful observations made by a Danish astronomer named Tycho Brahe. Okay, so this is all scaffolding of knowledge, measurements and observations, and then explanations of observations, and then underlying explanations of those observations. So Newton came up with a more basic law, the law of gravitation, and from that law he could derive all the laws of motion that Kepler derived from observing data. Okay. So, and in that act, by writing the law of gravitation, you know, the story about Newton watching the apple fall is probably just a fable. But by understanding gravity, Newton basically unified the earth with the heavens. So the same force that makes an apple fall to the earth makes the moon go around the earth, and makes the earth go around the sun, and all the other planets go around the sun. And this is after Newton's time, but then later astronomers realized the sun's not the center of the universe either. The sun goes around the center of our galaxy, the Milky Way, and our galaxy is not the center of the universe. Our galaxy is one of 100 billion galaxies at least in the observable universe. So, you know, we're just a speck within a speck within a speck within the whole. Okay. And then, well, I overlooked this gentleman here, Albert Einstein, who explained gravity even in a more basic way, more fundamental way than Newton. Explained that gravity is not a force as we usually think of it. That gravity is Einstein kind of showed that time is another dimension, that space doesn't only consist of 3 dimensions. It also has a 4th dimension, which we experience as time. And this unification of space and time led Einstein to describe gravity in terms of geometry of a 4-dimensional space-time. And he made more accurate predictions than Newton did. So Newton's physics is perfectly good for us to send probes to Mars and successfully land them on Mars, and even send probes out to the outer planets like Jupiter, Saturn, Uranus, and Neptune, and even to Pluto. But when you start talking about neutron stars and black holes, Newton's gravitation breaks down. It doesn't work under those conditions very well. Whereas Einstein's gravitational theory works under those extreme conditions and works under the normal. It simplifies. If the gravitational force is weak, then you get Newton's equations out of Einstein's general theory of relativity. But when the force of gravity is very strong, then you have additional modifications that Einstein's theory accounts for, but Newton's doesn't. Okay. And, you know, I've mentioned this in the discussions that we need Einstein's theory of gravity to make corrections in the clocks that are on, you know, the devices that keep time on the satellites that we use for GPS navigation. If we didn't know about relativity thanks to Einstein, then GPS would not be accurate at all. We couldn't, you know, we couldn't use Google Maps and stuff like that. We need Einstein for that. All right, and this is just an illustration kind of showing the different models. So you go back to Copernicus, and he assumed the sun was right at the center and all the planets followed circular paths. You see the Earth and the moon going around the Earth, and then the Earth-Moon system going around the sun. And further out from the sun is there's Mars, there's Jupiter. Further out, there's Saturn. Then the model on the right is from Copernicus. That's not Copernicus, Kepler. He modified Copernicus's model to have elliptical paths. It made more accurate predictions of where the planets actually should be at a certain time. You know, all this was important for, a lot of this was motivated by better navigation. Just think of when this was done. This was like in the 1500s, 1600s, when explorers were crossing the oceans. You know, 1492, Columbus sailed to America, and kind of started the age of exploration. And better navigational methods, better maps were needed. And a lot of navigation was based on stars, stellar navigation. So they needed to understand, and planets, they needed to understand what was going on in the sky very accurately to get around the Earth more accurately. All right, so Einstein's theory of gravitation, like I said, is more accurate than Newton's, but that difference only really is noticeable when the gravitational fields are very, very strong, like near a neutron star or a black hole. So under normal conditions, Newton's theory of gravity is perfectly fine. And this is what it is. It says that the force of gravity is equal to a constant. It's called the universal constant of gravitation. It's the same number. If we measured gravity on Mars, we'd use the same formula, same constant, just different masses. And the d in the bottom is the distance between those masses. So if I have two masses here, if I know the masses and I know their distance apart, I can calculate what the force is between them very accurately, okay, thanks to Newton. Now, in Newton's time, they were, they could do a very good job calculating distances, and they could do a very good job calculating masses, but they didn't have a very good idea what the strength of that, what the size of this constant was. It's kind of an educated guess. It's a very small number because actually gravity is a very weak force. It's the weakest of all the forces that we know of in nature, by far, actually. So it was up to later scientists to measure this constant so they could make more accurate predictions of the strength of gravity. And one of these scientists was Henry Cavendish, shown here, and this is the instrumentation he used. It's a very brilliant device. It's called a torsion balance. And what he did was and you see when he was doing this, it was like in the 1700s. It's about 100 years after Newton, and and nevertheless, it was a technological marvel, you might say. What he had was I wish I could pause it here. I don't know if I have a way to pause this oh, I did sort of pause it. Let me try that again. Try to pause this animation. There we go. All right. So what you see here is just a beam holding a wire, and on that wire is balanced what looks sort of like a barbell. There's a beam there with two masses on there, and he used, I think he used lead balls. I'm not sure. Lead balls, maybe iron balls. I'm not sure. Something heavy, some heavy metal on those, balanced on a fine wire. Also on this balance, you see here, it's kind of hard to see maybe for you, but there's actually a mirror. You put a mirror on there, and you see here a light. And it was probably, I don't know if you used a gas flame or a candle, but there was a light and the hole there, so it illuminated this mirror with a narrow beam of light. If this wire would twist and these weights would move, that mirror would reflect the beam of light to some other location, right? You'd be just basically turning that beam. Now, on the ground were mounted very massive balls, and these balls were rotated very carefully toward the balanced balls. So let me try to show that. Okay, so there's the beam of light hitting the mirror. Okay, that beam of light reflects off the mirror, and you're going to see in a moment that it falls on this curved scale. When those masses are moved toward the balls are attracted to the masses by the force of gravity between them that twists that wire and moves reflects, the mirror moves, and that beam of light moves across this scale. And by doing this, because he had such a long lever arm, a tiny twist in this made a measurable distance change on that scale. And by this method, Cavendish could measure the strength of the force between those balls. If he knew he knew the mass of the balls, and he could measure the distance apart. So if he knew the distance and the mass and the strength of the force, the only unknown would be that gravitational constant, which you could easily solve for at that point. So Cavendish did that, and he came up with a value very close to the modern value, which is about 6.67 times 10 to the minus 11. So a very tiny number. Okay, so that's Cavendish's contribution to the historical development of our understanding of gravity. Okay. We can even show, thanks to Newton, now we understand Galileo's experiment. He dropped two different balls, one heavy, one light, from the top of the Tower of Pisa, and they fell at the same rate. They hit the ground at the same time. Before that, no one had done the experiment. Aristotle thought, well, if a ball is twice as heavy as another ball, then the one that's twice as heavy is going to fall twice as fast. That's not true. It falls at the same speed. Neglecting air resistance. Obviously, a feather falls slower than a cannonball, but if I put the feather and a cannonball inside of a vacuum chamber and pump all the air out, they both fall the same rate. And if it comes up in the discussion, I might show a video of that. Okay, so anyway, I won't go through the math. If you remember your algebra, this is like 7th or 8th grade algebra. You can show here that all objects fall to the earth at the same rate, which is the acceleration of gravity, which is about 9.8 meters per second squared. Okay, now this is one of the great triumphs of science and Newton's gravitation. Once Newton published his theory, it made sense to a lot of people, but that didn't mean they accepted it blindly. They wanted to test it. So they kept coming up with different ways to test it. And they started, measuring, just like Kepler did, studying the motions of the planets. But, this was later. They had more advanced equipment. This telescope at the time in the I wish I wrote the date here. Neptune was discovered, I don't know, in the late 1800s. This is bugging me. Let's go to good old Google. (1846), so the mid-1800s. Okay, by the mid-1800s, they had much better telescopes than in Kepler's time or Newton's time. Where was I? There we go. And this was called the Dorpat refractor. It was in Berlin, and it was made by Josef Fraunhofer, who was a great German optician. It was the best telescope of the time. And anyway, astronomers throughout Europe were studying the different planetary motions, and they noticed a discrepancy in the motion of Uranus, at the time, the most distant planet known. They observed it, night after night, and based on Newton's gravitational theory, they would predict, if I see it at that location tonight, then let's say 5 weeks from now, I can predict precisely in the sky where it will be. Well, when they did that, it wasn't quite there. There was a discrepancy, and they thought, oh no, Newton's wrong. But some people, like Urbain Le Verrier, right down here, a French mathematician, physicist, astronomer, said, well, I think Newton's probably right, but we could explain this a different way. Instead of gravity being wrong, maybe there's another planet out there influencing Uranus with its gravity, right? So they're interacting gravitationally. So he applied Newton's theory of gravity to explain this discrepancy in the orbit of Uranus. And based on that, he predicted where that planet should be. Well, he had been a student of this guy on the right, and this is a great tale of international collaboration as well. Germany and France, at least in modern times, were never great friends. Well, nowadays they are. They're good friends, but in the 1800s they weren't very good friends, and in the early 20th century they didn't get along that well. But that didn't stop scientists from being friends. And Leverrier sent his calculations to his good friend up in Berlin, Johann Galle, who had access to the best telescope of the time. And Leverrier said, hey, Johann, I think Uranus, its motion could be explained by a new planet. And on the night, on a particular night, and he gave the day, he said, on this night, I predict this planet will be in this location. Can you look? So Galle aimed his telescope in that direction, and within a degree, 1 degree of the predicted position, he discovered Neptune. So by using gravity and its effect on a planet, a whole new planet was found. It wasn't found by looking for it. It was predicted to exist. And then when the prediction was tested, there was indeed a planet there, and that was Neptune. Neptune was not known to humankind before that, and would not have been found if it hadn't been for Newton's gravitational theory. That's to me an amazing story. That's almost like magic, that you can, you observe one thing and there's this invisible influence on it. And to explain that invisible influence, you say there's a mass in a certain location, and when they looked, there was Neptune. Okay, so that's the end of my little story about gravity. Of course, it's a huge story. I could go on and on and on, because we're only going to the 1840s, right? Basically. But let's go and look at our simulation. So let's get to our class. Let's see, nobody else has joined us. Okay, it's just Karen and myself. All right. We're in week 5, theory of gravitation, summative assessment. This is actually one of I like all the simulations, but I like this one in particular, I think. So as always, download the assessment guide, which are the instructions. If you don't see it pop up, go to your downloads folder, open the assessment, because I still get the feeling that some students do not look at the guide. They just don't follow directions for some reason. So anyway, downloads folder. All right, let's see. Drag it over here and start following directions. It says visit the gravity force lab. So I'll do that. Observe and note the mass of mass 1 and mass 2. Okay, I'm not going to give any numbers away. You can see it for yourself. The mass of mass 1 is whatever it is. Write that down in your essay. Write the mass of mass 2. I recommend, you see some very tiny numbers here, 0.0000001666852. That tells you, okay, I'm going to give away some numbers. Why not? If I have 2 masses, one's 100 kilograms, that's about the weight of a large man, and the other one's 400 kilograms, which is the weight of an extremely large man, or maybe a small car or something, then if I put those, let's just do it here. Let's just do an experiment. I'm going to take Newton's formula. Remember Newton's formula? It's, well, I'm going to go by memory. We take the product of the two masses, so I'm going to take 100 times 400. Okay, that's a pretty big number now, 40,000. I'm going to divide it by their distance apart. Now I have this, I moved this meter stick so I can measure directly their distance apart. So these are 4 meters apart. The centers are, you measure from center to center. They're 4 meters apart. I'm measuring from the balls. These little stick figure men have nothing to do except hold these balls in place, okay? They play no other role. You could ignore them. They're just they're just there to hold those balls in place. You could just as well have glued the balls to the floor, okay? So I'm going to divide that number by that distance squared. Okay, well, I get 2,500. But remember, the formula that Newton has, let me show it to you again, was this. Product of the masses, that gave me 40,000. I divided by 16. That gave me the number I just said. What was it, 2,500? And then I have to multiply by this constant. And that constant, as I recall, is 6.67 times 10 to the negative 11, approximately, okay? All right, there's the number. I'm going to put it in scientific notation so I can read it more easily. Where do I do that? There we go. 1.667, let's call it 1.67 times 10 to the minus 7. That's what that says. Let's look here in our simulation. It's kind of hard to say what that says because it's such a small number. Let's put it in scientific notation. There's 1.67 times 10 to the minus 7, just like this. I mean, if I round this off, it would say 1.67 times 10 to the minus 7, same number. So I predicted using Newton's gravitational theory, the force between these two balls. If I had two real balls, it doesn't matter what they're made of, but if one's 100 kilograms, the other's 400 kilograms, and they're 4 meters apart, that is the force between them. I could make them out of concrete, I could make them out of lead, I could make them out of feathers. If that's their mass, that's the force between them. It's as simple as that. It doesn't matter if they're spinning, it doesn't matter if they're hot or cold. The only thing that matters is mass and distance. Okay, very important observation that Newton made. Some people think Earth's gravity comes from the fact that it rotates around its axis, but that's not true at all. I mean, Venus almost doesn't rotate on its axis. It's about the same, similar mass to the Earth, and its gravitational force is about the same as Earth's. If you stood on Venus, you'd weigh just about the same, a little bit less than you do on Earth, and the only difference is Venus isn't quite as massive as Earth. All right. So I did the first thing. Okay, again, we noted the distance. We already did that. The mass and the distance and the force, right? There's the force. You see the blue, and the color doesn't matter. In fact, the size doesn't matter. Only mass matters. I can click this for constant size. So now you don't get confused about the size difference. You see the force is still the same. Doesn't matter. Only mass matters and distance, not size. All right, so I want you to record these numbers and notice also that this force, so this blue ball is attracted to the red one with the same amount of force as the red one is to the blue one, even though the red one is heavier, more massive than the blue one. So think about that. There's actually a very fundamental reason why that's true. Change the distance between M1 and M2 by moving the masses apart. So I'll just, I'll go out to 8. That's as far as it lets me go. I'll go to 8 meters. I could go that. I can bring that one out. So there we go. Line them up. That's 10 meters apart. So at 10 meters apart, you see what the force is. Okay, I won't say it. You draw your own conclusions. Okay. Change the mass of mass 2. I guess it's up to you. It's probably best to just leave them where they're at or bring them back to where they were originally at and change the mass. Okay. Make it significant. Go to 1,000. Look at that. Okay. So that changed the number, changed the force. And that's it. I mean, if you want, you can change the mass of the other one too. All right. So that's basically what you do in the lab. And then, as usual, you describe what you did in your own words. Describe what you saw, include some numbers like forces, distances, and masses. Did you have any questions? Even if you think you know the answer, you should ask a question. If you know the answer, go ahead and answer your own question. Discuss 2 specific ideas from the reading related to the observation. So Feynman talks about gravity. What does he say about gravity that you can relate to what you observed? And then, did you discuss how the simulation contributed to your understanding of the theory of gravitation and its historical development? Well, I talked a lot about its historical development. I mentioned people like Aristarchus and Copernicus and Kepler and Galileo and Cavendish, and of course Newton. Newton goes without saying, but you know, Cavendish played an important role by measuring the gravitational constant. Kepler had the planetary laws of motion that were necessary for Newton to realize that the force varied as the inverse square of distance, etc. Okay. Make sure you list your references. Check your spelling, punctuation, stuff like that. Read it out loud to yourself and or to a friend so that you know that it makes sense before you submit it. Okay, and you might catch some typos that way. And that's it. I've said all I had to say. Any questions out there?
No.
All right then. I won't hold you any longer.
All right.
If you're happy, I'm happy, and I'll say goodnight. And you know, we have a few more days together in this class, but I wish you and everyone out there a happy Thanksgiving.
Happy Thanksgiving to you too.
All right. Good night.
Good night.